All right. Um, Okay. Hello everybody. So I'm Jaden. I'm one of your TAs for this class, and I'm going to give you guys a little exam one review. This will be recorded, so if you guys aren't able to stay for the whole thing or any reason, you'll be able to find it online after. I'll post the link and we can just go ahead and get started. So first question here is what's on the exam? So you're gonna have to know.
Okay, I was trying to, it wouldn't let me paste, it just kept pasting as like an image. Yeah.
Okay. So first question here was what's on the exam? So you're gonna have to know the parts of the computer, know what a CPU is, know that a computer has memory, know that there's a keyboard, there's a mouse, know all the parts of the computer. You're gonna have to know your performance equation, which is gonna be, and I'll get into this later. There's gonna be slides on questions similar to these about your instruction count times your cycles per instruction times 1/your clock rate. Know your speed up equation, know that it's a ratio, know those things. And all these things I'll get into later. Your reduced instruction set computer versus your complex instruction set computer. Know those little benchmarking sheets I'm sure you guys have seen like not only in discussion, but like in lecture and stuff. Know how to read those, know what those mean. Sign integers, know how to do negative numbers and binary, choose complement, and then know simple ARM instructions like how to add numbers, shifting left, shifting right, and then some data transfer instructions like load and store. So this is everything you need to know that will be on the exam. If you know all this stuff, you'll be good to go. There's not going to be any curveballs or anything like that. So for the exam specifics, it'll be 8:20 to 9:10 Monday on February 3rd. You're allowed a formula sheet, typed or handwritten, both sides, any font, anything you want can go on there. Um, just you can have one of those, and then make sure you have your calculator. Make sure your calculator's charged, pencils, scrap paper, pens, anything you would need. Make sure you bring it. Um, and this is Monday, so put it like in your calendar and don't forget. These are all of the times. So she's going to post this on Canvas, but you can also just look at it here. This is your section number and what time the exam is. It says 8:20 to 10:10 here. I think that's a typo. It should be to 9:10. It's not a 2-hour exam, but these are the areas, Chem Lab, CSE, Turlington, Weimer. You can find your section number on Canvas. So just, or not on Canvas, but on like 1.uf. So go on 1.uf, find your section number, and then find which room you're in. Make sure you go to the right room. That's really important. And then this next thing, this is probably different from your other classes. So download Gradescope on your phone. What's going to happen is when you're done taking the exam, you're actually going to take a picture of the exam, like all the pages, and scan it and upload it on a Gradescope. And the reason for this is it makes it a lot easier for us to grade. Like you guys are going to get your scores back pretty fast. And it's just because we can literally just go on Gradescope and mark things off like so quickly. So make sure you download this before you get in there. Make sure your phone's charged, make sure everything. But download this. It's really important. You need this to upload your exam. And if not, like it's more confusing. So just make sure you download this app before you get there. It's also bad when you're done taking the exam and then at the end of the test, you have to go to the front of the room and then everyone is just like waiting for you to download Gradescope on your phone and the Wi-Fi is like really slow. So just like download it both beforehand so it's like easier to know. But that's everything on like the logistics of the exam. They don't have any questions on that? Or okay. So I'll start get going into the content now. So the first thing up is the von Neumann architecture. So the first thing you're going to want to ask yourself is what exactly is computer architecture in the first place? Well, it's going to be how we interface with our CPU to access memory, uh, run programs, everything like that. And this guy, von Neumann, decided that he wants both instructions and data to be stored inside the memory unit. He decided that if everything was in this one place, you can send it to the data path, it'll perform on the ALU, the control unit, and then send it back to the memory unit. It's good if we have everything in one place. He could have decided to maybe let's have instructions in one area and then maybe like data in another and separate it that way. But he decided, okay, let's just keep instructions and data both in one place and then interface this with our data path and our control unit. So your data path is where your calculations are actually going to happen. This is where your ALU is. When you have two numbers in ARM instruction, you're going to add register 15, register 16 together. This adding is going to happen on the ALU, which is in the data path. The control unit, on the other hand, is what tells the ALU what to do. So it's going to fetch instructions from the memory unit, right? It'll fetch an add instruction. So let's just say, for example, in our memory unit, we have an add instruction, which is going to add 5 and 6. The control unit is going to take that. And remember, registers are always on your chip. And it will say it adds 5 into register 15 and then 6 into register 16. And then it's going to tell the data path or your actual processor, hey, let's add these two things together. Add them together, you get 11. And then it will send it back to the memory unit. That's kind of a general, very brief, very conceptual overview of what's actually happening in this architecture. And remember, it's the instructions and the data that are stored in memory unit. Everything is stored there. Any questions on the architecture at all? Okay, so this is the next big thing, which is going to be your complex instruction set computer versus your reduced instruction set computer. So your RISC instructions are very, very simple. Typically, they're only going to have one clock cycle. They're going to do one thing and one thing only. They're very, very simple instructions. And what's good about this is that when it's sent to the data path, it's sent in the yes, the control unit sends data to registers. The registers are on the chip. They're actually in the CPU. So yeah, so your reduced instruction set architecture, these instructions are very, very simple. And what's good about this is the hardware to actually decode it, or for example, the controller, it's very easy for it to do because all the instructions are simple. If you look on this right diagram here, all of these instructions are very, very short. They really only do one thing. I will upload the PowerPoint after this, and then you guys can see it. But yeah, so anywho, the instructions are very, very short, and it's very easy to decode, which means it's cheaper than a CISC instruction set. The downsides of this is when accessing memory, you can really only do it with load and store. So let's say, for example, you want to add two numbers. You would have to load one number from memory and maybe put it in a register. You would have to load another from memory and put it into another register. And then you would need to add the registers together and then finally store it back into memory. It took 4 instructions just to do this simple add procedure, right? And this is a very conceptual overview. Like every processor is different, so this is going to be different anytime you program this. But just for a general understanding, it would take multiple instructions to do one thing because they're very, very simple at the most fundamental level. But a benefit of this, again, is you're going to have more registers since you have to store more stuff in your CPU because there's more you have to do. So that's a good question. So someone asked, is the result sent to another register or is it sent straight to main memory? So what's going to happen is the addition is going to happen and then it'll be put into a register. So typically your syntax is like add and then your destination register and then what you're adding. So here, the result of adding 16 and 17, which in this case was up here, will be stored in R17, which is on the chip. And then after that, we store R17. So it'll be sent to another register and then sent to main memory after in a RISC architecture. And now the CISC architecture is pretty much the opposite. So these instructions are much more complicated. They do a lot more stuff, which means that it's likely that they're combining multiple RISC instructions together, for example. There's different addressing types, different ways to access memory. As written here on the slides, memory access is from different instruction types, which means instead of only using load and store to actually get data into the CPU, you're able to do it pretty much directly in the instruction. So if you remember before in the risk instruction, it took us 4 lines to add 2 numbers from main memory. This one, you could probably just add 2 numbers in memory like this and do it all in one instruction. But this instruction is much more complicated. As you see down here, it's a lot of code just to run one thing, which means that the hardware to decode it is much more complicated and much harder to do. And again, these aren't real instructions per se. It's more just an example to show you the types of instructions that a RISC or CISC processor would have. Your computer that you're using right now, if it's not like a Mac or anything, it's probably CISC. x86 is always CISC. And then RISC is going to be like your ARM computers, or if you have super small electronics, those are typically RISC processors. Any questions on RISC and CISC instruction sets? Okay, so I'll go to the next slide here. So this is going to be your timing questions. Every time you see one of these questions, the first thing that should go to your head is this formula. Instruction count times cycles per instruction. Sorry, it's kind of hard to write with my mouse, times 1 over the clock rate. And cycles per instruction is the same thing as CPI. I just write it as this because it's good to write the units, and I'll get into that in a second. But we're considering 2 implementations of the same instruction set, which means it's either both RISC or both CISC. They're the same thing. It gives us the clock rate of both processors. P1 is 2.5 with these CPIs. P2 is 4 gigahertz with these CPIs. And it gives us how many instructions there are and how the program is divided up. This isn't really necessary to solve the question. However, if you want like a conceptual overview of what this means, Class A instructions could mean like something simple like adds or something, and then maybe Class D instructions are loads. And all these types of instructions take a different amount of time to execute, which is seen here. Like these A will only take 1 clock cycle, where these D will take 3 clock cycles on processor 1. So you can think of a program with 50% of it as D instructions, and then the rest as just A, B, and C accordingly. And that's kind of just like a conceptual understanding of what this question is asking. How can you run a program with those type of instructions? So the way you do this is the first thing you're going to do is you're going to take a weighted average. That's going to be your CPI. So you're going to take each of the CPIs that are given, and we're saying 20% of the time, the instructions are only going to take 1 clock cycle. So you do 0.2 times 1. 10% of the time, the instructions will only take 2 clock cycles. So you add 0.1 times 2. 20% of the time, it'll take 3 clock cycles. So we can add that. And then 50% of the time, it will take 3 clock cycles. So you just add 0.5 times 3. And that will give you your average CPI, which is your cycles per instruction. And that is given here. It ended up being 2.5. So when you're writing out this formula that I wrote up here, which you can also see here, and it gives you seconds, always write the units. That's the biggest thing I can stress here. The units will always nicely cancel. So let's say you forget the formula, but you have a cheat sheet, so you probably shouldn't forget the formula. But let's say you write it down wrong, or you write your numbers down wrong, then the units will cancel out nicely and you'll know you have the right answer. So this 1500 instructions per program, this comes straight from the question, which you can see. This 2.5 cycles per instruction, this was the weighted average of all of our CPIs for processor 1. And then our clock rate was 2.5 times 10 to the 9. And that was this part right here. This 1 over clock rate is how I like to write it. But in this example, it's just divided by the clock rate. And clock rate is always cycles per second. So make sure you write your units. Everything will cancel, and you will end up with seconds per program. And that is for processor 1. So processor two is going to be literally the exact same thing, except you're going to use different CPIs for your weighted average. So here, instead of like times one, times two, times three, everything will just be three, which you'll see like the average of this is just three, no matter what the weights are. And then someone asked what kind of calculator you should get. If you have like a scientific calculator, that's probably better. Um, with a for function, I don't think you can do like times 10 to the ninth. So like a scientific calculator or a graphing calculator is fine. You don't need anything like too fancy, like nothing crazy, but a scientific calculator is good. Just like a TI 84, I think it's called. So yeah, you'll see that the average here is going to be three. So for P2, your average is three. And all we're doing is we're repeating this same formula over again. So instructions per program, instructions cancel, cycles per second, cycles cancel, and you end up getting programs per second. And again, this formula is your instruction count times your CPI times 1 over your clock rate. And that gives you your seconds or your T. So have those memorized. Super important. And then whichever one the question asks, which is faster, well, this one's faster because it takes less time. Or this one takes less time, so it's faster. But yeah. So now you want to know what the speed up is of P2 if class A instructions are improved to a CPI of 1. So if you recall, your speed up is going to be your old time over your new time, right? And all this is a ratio, right? There's no units to the speed up. So if we write the formula over each other, the IC of the old processor times the CPI of the old processor times 1 over the clock rate of the old processor over our instruction count of the new processor times CPI over the new processor times 1 over the clock rate. If the instruction count of both of these are the same, we can just cancel it out. If the clock rate of both of them are the same, we can just cancel it out. And the only thing you have to recalculate is the CPI. So here we recalculated 2.6. And then since the IC and the clock rate have not changed, we can just take the old CPI and divide it by the new CPI. Does that make sense to everybody? How you can kind of skip steps in the calculation if you know what they are, or if they haven't changed between improvement of instructions. So yeah, the biggest thing with this is know that this is a ratio, right? This has no units. You're just trying to see how much faster is the new computer when compared to the old computer, right? So that's how I find that. Recalculated the CPI and then just did the old time over the new time. That's a good question. So someone asked, why did it say P2 has CPIs of 3333 instead of just saying it has one CPI of 3? The reason for this, I think, is just because in P1, you can see each of the CPIs are different. Like A has 1, B has 2, C has 3, and then D also has 3. It's just saying that they're all the same and just giving a corresponding one. So A is 3, B is 3, C is 3, and D is 3. And it just says 3333 instead of saying they're all 3, or instead of giving them different ones. So that is your timing questions. So really for these, just memorize your formula and write down your units. Writing the units is probably the most important thing because even if you don't know the formula, you could probably end up deriving it just by writing down the units. So that's really important to do. So this next question is asking, what if we improve the CPI and we improve the clock rate? So what happens here is we recalculate our CPI like we did before, because A is 1, so it'd be A, 1, and 3 times 0.8, because we just added all these together. So recalculate your CPI, and then your speed up this time, since the only thing that hasn't changed is the instruction count, we just do the CPI of the old divided by the clock rate of the old over the CPI of the new divided by the clock rate of the new. So someone asked, what does it mean to improve the CPI by one? So it's improving. So what CPI stands for is it stands for cycles per instruction. So cycles is how many times your clock is going to like cycle through every time you want to run an instruction. So here originally, every time you wanted to run an instruction from class A, it would take 3 clock cycles. What's happening here is it's improving it to one. So instead of, let's say, you run add and it takes 3 cycles to run add, it will only take 1 cycle now. So you have to recalculate your average. So that's why that's what it means to improve it to one. So yeah, with these, again, just a ratio. When you're doing these ratios between old and new processors, you don't need to recalculate the entire formula. Yeah, it means to 5 GHz in this. But the thing is also is if we didn't say 5, actually, never mind. Sorry. I was gonna say that the gigahertz would end up canceling out, but yeah, it just means clock rate is improved to 5 GHz. Yeah, so you will have to be careful of gigahertz versus megahertz and all the other units. I recommend honestly just writing them down on your formula sheet because you'll end up losing points if you don't know them. The biggest ones to know are like mega is 10 to the sixth, giga is 10 to the ninth, no nano, which is -9, and then pico is important as well, and like milli. Honestly, just write down like the whole scale on your cheat sheet, just somewhere small in the corner, just so you don't mess it up in case it asks for a specific form. Okay, so this is the benchmarking website. I'm going to switch my window so I can show you guys this. Okay, here we go. Okay. Can everyone see this? No, the old cheat sheets are not posted anywhere. So this is your benchmarking sheet. So get familiar to seeing this because it tells you a lot of good information. So the most important parts of this are right here. You get your just normal clock rate in gigahertz. But this is more important in the top. So somewhere random, there is some computer that this company decided to compare every other computer to. Just a base computer, base performance, just a computer somewhere. What this number means is it has no units. It's a speed up. It's a speed up of this Asus R672 something processor compared to that base processor somewhere. So what this number means is that in base performance, this processor is 2,410 times faster than the base computer. And base performance just means you're like on the web, you're just on your computer, like messaging your friend or something. Peak performance would mean like you're overclocking, you're trying to push your CPU to its limits, like as hard as you can to get super, super good performance. This is like the best it can possibly do. And what this number means is again, it's 2,660 times better than the base computer. And it's good if you just get that same like wording in your head. Just that many times better than the base computer. The next part that's important is your megahertz over here. This is how fast your CPU is. So your max megahertz is going to be 3.7, and this is peak performance, right? Peak clock rate. And then nominal is just going to be your normal 2.2, 2,250 hertz, megahertz. These are the same unit. So those are like the three or the two biggest things you need to know. Know how to read this benchmark number on the right, know how to get the hertz of your CPU. All this stuff is kind of just the numbers it gathered from the benchmark, what operating system the test will run on, the compiler, how big your cache is. So nominal is just going to be like your normal performance. Just like if you're like browsing the web or something. And then max is like peak performance. So like base and nominal are like the same thing. So yeah, and if you guys are confused about this, there's like a bunch of different processors. You can just kind of look and see, you know, how they are if you're confused. But there's also examples like this in the discussion slides and in here. So just know how to read this speed up. Remember, this is a speed up. You know how to read these hertz. So I will go back to the slides now. Yeah, the exam is mostly free response. There might be like some multiple choice questions every once in a while, but for the most part, it's just pen and paper. It'll ask you a question. Sometimes you'll have to do some math for response. You can put images on your cheat sheet. They're allowed to be handwritten or typed. So you can type them up and just print them out at Marson or something. So this is what I was talking about here. This is the exact same sheet we just saw basically. It doesn't have the clock rate down here, but you may be asked that sometimes. So up here again, top right, this is your speed up. On average, this platform is 200 times faster than the base machine. That's what you need to know. It's a speed up, whereas the old machine is the base, and the new one is like this one that it says. So, and then here's your clock rate. I don't believe there are any practice exams posted. However, these review slides and the discussion slides and the homework, um, in general are very similar to what you'll be seeing. So does anyone have any questions on these benchmarking questions? I think they're pretty straightforward. Just know how these speed ups understand and know your clock rate.
So will we be asked about the clock rate on that on those charts?
Yeah, it'll be similar to what you've seen like in discussion and homework. You could be asked speed up, you could be asked clock rate. Maybe you could be asked like what OS was it ran on, and then that literally just said OS. Like it'll just ask you a question about like something on here. But the biggest ones are the speed up and then like how fast your clock is. So next we're gonna do some binary number arithmetic. So on this screenshot, it doesn't say it, but um in the like the website I just showed you, it says it like on the right here. I can show you again. Typically you won't be asked this. It'll mostly be like clock rate or the speed up, but just in case you wanted to know, it's right here. Okay, so now we're gonna do some binary number arithmetic here. So I guess first I'll just start by giving a very simple introduction to how to actually read binary in the first place. So let's say you have the number. Let me get rid of this 'cause I messed up. Um, let's say you have the number that you're all used to reading 123, right? You're aware from like elementary school that 3 is the ones place, 2 is the tens place, and 1 is the hundredths place. So you could rewrite this as 3 times 1 plus 2 times 10 plus 1 times 100. You guys are very used to doing this. And this can be rewritten as 3 times 10 to the 0 plus 2 times 10 to the 1 plus 1 times 10 squared, right? So it's a simple way of rewriting the number. When you have a number in binary, it is the exact same thing, except instead of doing times 10 to whatever the position is, it's going to be 2 to whatever the position is. And instead of multiplying by like 3 or 4, it's just going to be whatever this number is here, since you can only have zeros and ones. So this number, 1011, is going to be, you look at the position, this is position 0, 1 times 2 to the 0, because there's a 1 there, plus 1 times 2 to the 1, because there's a 1 there, plus 0 times 2 to the 2, plus 1 times 2 to the 3. And that will give you 8, 9, 10, 11. So this is just simple how to convert a binary to decimal. Hopefully you're all at least slightly aware or have seen this before, right? Nothing new. So in this question, we're going to convert the other way around. So 2's complement is how we represent negative numbers in a computer. And I'll go ahead and show you how to do this. So when you're starting these questions, ignore the negative sign, right? First, just convert the number 103 into binary. And the way to do that is I recommend writing out all of your powers of 2's. So 1, 2, 4, 8, 16, 32, 64, 128. Just write them all out. And we look at 103 and we say, what is the biggest power of 3 or power of 2 that can go into 103? And is it 16? No, because we can do 32, we can do 64, but we can't do 128. So 64 is the biggest power of 2 that can go into 103. So this is 2 to the 6th. So we have 1 times 2 to the 6th. And then what we're going to do is we're going to do 103 minus 64. Let me just see what that is, which is 39. So now we look at 39 and we say, what's the biggest power of 2 that fits into 39? Well, that would be 32. So we do plus 1 times 2 to the 5th. And then we subtract 32 from 39 and we get 7. And then we say, what's the biggest power of 2 that goes into 7? Well, it's 4. So we do plus 1 times 2 to the 2 minus 4. We get 3, and that would be 2. So plus 1 times 2 to the 1. We get 1 plus 1, which is 2 to the 0. So we have this string here of 2 to the power, and we just write down, if there's an exponent here, we put a 1. If there's no exponent in that position, we put a 0. So 1 in position 6, position 5, we have a 1, 3, and 4 are going to have zeros. And then 2 is going to have a 1, 1 will have a 1, 0 will have a 1. So this is your number in binary. But the question asks for 16 bits. So if the number is positive, you extend it with zeros. And if it's negative, you extend it with ones. So remember at the beginning of this question, I said, at first, just until you get it in a binary form, treat the number like it's positive. So we're going to extend with zeros. So we have 1, 2, 3, 4, 5, 6, 7 bits here. So we're going to add 9 zeros. So like this. And this will be your number, positive 103, written out in binary. But the question isn't asking for positive 103, it's asking for negative 103. So what you're going to do is you're going to flip all the bits. Every time you see a 1, you have a 0. Every time you see a 0, you see a 1. So 0, 0, 0, 1, 1, 0, 0, 1. And then these are all just ones. And in 2's complement, after you flip the bits, you have to add 1. So we're going to add 1 to this. And then finally, it wants it in hexadecimal, which means to convert to hexadecimal, remember A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. You just find this number in decimal, and then 0 through 9 is just the regular number, and then everything else is like A, B, C, D, all the way up to 15. So this here is A plus 1, which is 9, 9, F, F. So what if there's a right on the 1, we have to add 1? Okay, that's a good question. So let's add 1, 0. Okay, so let's say we have this string right here, 1, 0, 1, 1, and we want to add 1 to this. So you're gonna add this just like you would add any other number. So when we add one here, 1 plus 1 is 2. So we have to add a 0 and carry a 1. So 1 is 2. So we add 0 and carry a 1. The 1 would go here. So what basically essentially happens is you carry a 1 just like you would in any other like adding like base 10, but you're flipping all the ones to zeros until you reach your first 0. So like I can show you another one. 1 0 0 1. It would be 1 0 1 0. You flip all the zeros and then add a 1 at the next 0. Does that make sense? Okay. So yeah. So this is just kind of more typed out what I wrote because my handwriting is probably hard to read. But if you want some steps every time you see one of these questions, first, convert positive number to binary. That's the first thing you should do. Second, sign extend zeros because the number is positive at this point. 3, you complement it, which means every 0 you replace with 1, every 1 you replace with 0, and then 4, add 1, and then 5, 2 hex. Every time you're trying to convert to 2's complement, these are the 5 steps that you should take. So next question here is converting binary to hex. So we kind of did this a little bit in the other one, but I'll just walk through this one just so it makes more sense on converting a number to like decimal. So 0 1 0 1. I think I forgot to mention too, when you're doing these, always group them into 4s. So if you have like a super long string of like zeros and ones like this, group them into 4 at a time and then convert to hex that way. And like let's say you have like 3 on the end here, you can just like append a 0 and convert to hex. Yeah, so 0 1 0 1 is going to be 1, and this would be 2, this is 4, so this would be 5. And I got that from 1 times 2 to the 0 plus 1 times 2 to the 2 gives you 5. And then this is just 1. So OX 1 5 is your answer for converting this to hex. Remember, group them 4 at a time. If we had like 0 0 over here, just add 2 more zeros and then put a 0 down. Any questions on these binary, like adding binary, anything like that? Yes, you'll have to do hexabinary. So let's say you have the string OX BAFF. So remember, each of these represents 4 bits. So F is going to be 4 ones because remember F is 15 and 15 in binary is going to be 1 1 1 1. Just 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3. And then this one is the same thing. All ones. A is 10, which is 1 0 1 0. And then B is 11, which is 1 0 1 1. So you go 4 at a time and then just write out whatever decimal number that is in binary. Like A is 10, B is 11. And you should probably write that down too on your cheat sheet, like even though it should make sense. So this next part is kind of understanding how registers interact with the CPU. So first thing that you should get in your mind is that the registers are on the chip. So the registers are on the CPU. So if we want to get something from main memory, we have to load it in from memory with the load instruction. And then remember, because of the von Neumann architecture, this main memory has instructions and data, right? So if you have like a load instruction or something, it's in main memory. If you save like the string hello, it's in main memory. Everything is stored in main memory. So when you load, and this, like I said, registers are on the chip and they execute data from the registers. You have a load instruction. It takes from main memory to the registers. And again, this could be anything, it could be a number, a string, anything. Load is just you're loading a register with something from main memory. Store, on the other hand, is the other way around. You're taking something from the register and you're storing it in memory at some particular address. So load is main memory to the registers, store is registers to main memory. And then, yeah, I think this is just like a duplicate slide. So understand how that works. Understand when you're loading, you're taking it from main memory, storing, putting it back. So next, what you have to understand is how simple assembly instructions are working. So let me put white. I think it'll be easier to read. So this X3 here, this first number is basically always your destination register. This is where the output of these two operands is going. So when we do X1 plus X2, it goes into X3. Like it'll go into this register. So what we do is we look at X1. X1 is the number 1. Let me go back to red. X1 is the number 1. X2 is the number 4. And we just add them together and we store them into X5. Just like that. And remember, these are in hexadecimal. So like if you have like A5 here or like and like B7 here, I recommend converting it to decimal and then adding them and then back to hex to put it into the register. But you probably won't get something that complicated. Just or if you do, it won't be that big of a number. So that is for just adding, and then subtract would be the same thing and everything like that. The next thing you need to know is this LSR, and you'll also need to know LSL. So what these stand for is logical shift right and logical shift left. So when you're using these two instructions, you're shifting the bits in a binary format, not hexadecimal. If you shift it in hexadecimal, one, it doesn't even make sense how you would do that. Two, it'd be wrong. So make sure you convert it to binary and then you shift the bits. So again, the first one is always going to be your destination register. And then we're going to take what's in X1 and shift it 3 times to the right because it's a logical shift right. So let's go find it. Let register 1, which is A2. We're going to write that in binary. And then remember, in hex, you always have 4 bits for each digit. So there's our number. And then what we're going to do is we're going to right shift it 3. So if we shift it once, we have this. Shift it twice, we have this. And then shift it 3 times, we have this. And then what you're going to do is you're going to convert it back into hex. So 0, 1, 0, 0, 2, 0, 2, 1, 2, 2, which would be 4, and then 1. So 1, 4. Right there. Will move slash LDR not be on the exam. Know how to load, and then moving is just going to be like moving one register to another. So like if it is on the exam, it would just be like whatever's in X2, put it in X3. And then load, it would probably show you like the memory and like the addresses, and then you would just take whatever is at that address and put it into the register if you had like a load. For which one? The LSR or like the load? LSR, yeah. Okay, so just one more time. So when you see these questions, the first thing you're going to do is remember this is your destination register. This is where the output of this is going. So x1, we're shifting it right 3 times. So we go to x1 and we see we have a2, 0x, all these zeros, and then a2 at the end. So the first thing you're going to do is you're going to write that number out into binary format, which is 1, 0, 1, 0, and then 0, 0, 1, 0. And then what you're going to do is it's a logical shift right. You could also get like a shift left, but you're going to shift it right 3 times. And every time you shift something off, you just like replace the other side with zeros. So like here, if I just shift right once, it'd be 1, 0, 0, 0, 1, 0, 1. Here I append a 0, like because I'm gonna have an extra space. And then you do that 2 more times. And once you do that, you end up getting 0, 0, 0, 1, 0, 1, 0, 0, like after shifting all 3 times. And then you just convert this back into hex, which ends up being 1, 4, which you can see down here. Does that make sense? A shift literally just means like pushing the bits one way in that direction, and always replace with like zeros. And then yeah, so since the result was 14, it put 14 in register x2 because that was the destination register. So those are all the slides. When one shifts off the string, does it just get like deleted? Yeah, you can just think of it as like it's getting deleted basically. I'm not sure where it goes. It's technically like if you shift right, you're technically like dividing by 2, and a shift left is technically a multiply by 2. So you can also think of it that way. So does anyone have any questions about anything else? Okay, so I hope that was useful to you guys. Is there any instructions? Just no basic ones like add, subtract, move. It won't be anything too complicated. Or a logical shift left, logical shift right. Those stuff. So yeah, remember 8:20 Monday, February 3rd. And then if nobody has any more questions, I'm going to end the recording.